we can start. Okay, well, yeah, thank you everyone for coming. Welcome to this new session of our category seminar. We're very happy to introduce today's speaker, Michael Shulman from the University of San Diego, who will be speaking to us about Chu constructions and the calculus of multivariable mates. The title of his talk is Double Categories, Multivariable Mates, and Chu Constructions. We'd like to encourage everyone to make questions at any time during or after the talk. So questions can be asked in Spanish as well. And in that case, we would be very happy to translate for Michael. So yeah, please, Michael, take it away. Thank you very much.
Okay, thank you. Thanks for the invitation. I'd like to tell a story that starts with some more familiar things and moves through some slightly less familiar things, and maybe ends up at this thing called the Chu construction and what it has to do with double categories. So let me start with by just sort of talking about adjunctions and some things we can do with adjunctions. So the ordinary definition of adjunction between categories can be phrased as saying that we have a natural bijection between Homsets, like that, for objects of our categories A and B. And there are various ways in which we can generalize this to make it a little bit more sort of abstract and two-categorical. So one way that we can generalize it is that we can allow A and B to be functors rather than objects. And so what I mean by that is that I fix some category, say X, and then I have a functor, which I'll still write as little a from X to A and little b from X to B. And then what we have this is sort of X is sort of a generalized version of the terminal category, guys, because if X was just one, these would just be picking out objects. And then we have a similar sort of bijection between natural transformations from F compose A to B and G compose B to A. Or sorry, AA to G compose B. Right, so this is essentially just applying that same bijection pointwise, and it gives us a correspondence between natural transformations. So that's one thing we can do. And then another thing that we can do is to dualize that construction, because an adjunction can be described purely in terms of a unit and co-unit in a two-category, such as cat. And so we can take everything in our two-category and turn it around, because now these are just morphisms in the two-category cat. So now, instead of A and B mapping into a categories A and B, I can have some other things like, say, C and D mapping out of A and B into some other category Y. And then I'll have some bijection in a similar way between, sorry, it's going to go look the other way, maps from, let's see, so if I get this right, so if, right, yeah, like that. So A goes to B, okay, something like that corresponds to something like this. So maps from C, natural transformations from C to D compose F corresponds to G, C composed G mapping to D. So, and this is sort of because you can express this first correspondence in terms of pasting with the unit and the co-unit, you can do the same sort of thing in the opposite category and get the same sort of correspondence. And then you can combine this if I have two adjunctions. Say F is left adjoint to G and H is left adjoint to K, then I can put F and G after my A and B, and I can put my G and my H and K before them. So what I get is a correspondence between squares that looks like this, or bijection between squares. So I've got a pair of functors A and B go on the left, and the right, and I've got sorry, G goes the other way, and I've got my adjunctions H and K and F and G on the bottom and the top, and there's a bijection between two cells of this form and two cells of this form that I can get by composing with the unit and co-unit. So, for example, one way of, one direction, what I do is I have something like this that I can compose with that. This is a unit or a co-unit of that adjunction, and then I have something like this. I have a unit or co-unit of that. I think probably I wanted this one. I can never remember which is which. So if I have something like an alpha over here and I paste it with some stuff, and then I get a beta over here, and similarly. So this is sometimes called the Mate's correspondence, and we say that these two cells are mates of each other. This is sort of an Australian terminology, I guess. People in Australia sometimes call each other mate, and so they generalize this to refer to this correspondence. They call it these two cells are mates of each other. And when you start to see squares like this, then if you're the sort of person who likes double categories, then you might think, oh, that this is starting to look like a double category, because I've got one kind of thing going up and down. I've got functors, and then I've got something else going left and right. I've got adjunctions. So you can express this in terms of some operation on a double category. And this is nice because it gives you a nice way to talk about the functoriality and the naturality of this construction. So there's a double category of adjunctions where you have say the objects are categories, and the vertical arrows are functors, and the horizontal arrows are adjunctions. So they consisting of a functor in both directions. And then the two cells, the squares, are, you might call them mate pairs of natural transformations. So in other words, if I have a functors going up and down and adjunctions going left and right, then there's this bijection between two cells and one or the other. Given an alpha, I can construct a unique beta, and given a beta, I can construct a unique alpha. And then this sort of this bijection can be expressed as a theorem that, say, a two cell in this double category is determined uniquely by one of its components. That's one way of phrasing this theorem. There are other ways to do it. I mean, if you look back at the first reference for this, I believe is in a paper by, I think it's Kelly and Street on review of the elements of two categories. And there they do it by saying you have two different categories, double categories of adjunctions, where the two cells are defined in the two different ways. And then there's an isomorphism between these double categories that sends one two cell to its mate. But this is an equivalent way of saying that. Okay, so this is a nice use of double categories. But the generalization of this that I'm interested in is to the situation of multivariable mates. So what do I mean by multivariable mates? Well, it's multivariable mate is a mate that involves a multivariable adjunction. Right? So what is a multivariable adjunction? So a multivariable adjunction is something that involves three categories, A, B, and C. We've got three functors relating them, which you might sort of draw like that, although that's a little bit misleading because they don't go back to a product. But what they actually look like is they're each of the three functors has two of the categories in its domain and the other one in its codomain. So there's one going forwards from A cross B to C, and then there are a couple going sort of backwards from A and C to B, and from B and C to A. And in fact, for various reasons, technical reasons, the A's and B's that are moved over there get opposite. And then we have, we might call these, say, H and G or something like that. And the adjunction isomorphisms are that each of these functors can be compared. We can take a map out of the value of these functors to some other object of that category that it lands in. So we can fun maps from out of F of something into C. Well, I can transpose the F in two different ways. I can map in A into G of BC, or I can map in B out of little b into H of AC. So I have these isomorphisms. And the canonical example of this is the tensor and internal Hom adjunction in a closed monoidal category. Where in that case, sort of A and B and C are all some category, some monoidal category V, and F is this tensor two variable functor, and then G and H are some sort of internal Hom operations. If it's symmetric monoidal, then G equals H, or is isomorphic to it. If it's not symmetric, then G and H are sort of a left Hom and a right Hom that satisfy this universal property. So multivariable adjunctions haven't been studied as much as ordinary adjunctions and for as long, although, which is a little bit surprising because this sort of tensor and internal Hom goes way back to the beginnings of category theory. But I guess maybe this multivariable nature makes it a little bit trickier to write down formal structures. And so part of what I'm going to talk about today is what I think sort of the best formal structures are to describe what a multivariable adjunctions look like. But the point, I mean, so just before I say something about that, let me mention that there are sort of mates. There is sort of a mate correspondence for multivariable adjunctions. One way to talk about this is to reduce the multivariable adjunctions to single variable adjunctions. So you can say, like, for a fixed object, you can have like f of A blank is left adjoint to H of A blank as functors between B and C. And similarly, we have three other adjunctions, three other single variable adjunctions. And so we can talk about mates there, and that's good enough for some purposes. For example, one particular instance of multivariable mates is in the case when I have, suppose I have two closed monoidal categories and a pair of functors between them that are adjoint, then I may be interested in how this adjunction relates to the tensor products and the internal Homs of V and W. And there are lots of different things that you can say that may happen in different cases. But like, for instance, one of the particular cases that people are interested in is a case when you have a map that looks like this. So you have an A, so here A is in V and B is in W. And then if I take G of B, it maps it into V, and then I can tensor them, and I can map then with F all back over to W, or I could map A back over to W and then tensor it with B. I could have a map comparing them in that direction or in the other direction. And the Mate's correspondence, if you sort of flip things around here, it turns out that a map like that is equivalent to a map that compares G acting on internal Homs. So if I have two objects, B1 and B2 in W, then I can take their internal Hom and apply G to that, and then I get an object of V, or I can apply G to them separately and take their internal Hom in V, and I can ask for there to be a comparison map there. And so there's actually a bijection between comparison maps of this kind and comparison maps of that kind, and that's given by a Mate's correspondence. So this over here, if this one over here is an isomorphism, then that's talking about G being a closed monoidal functor. And this one over here being an isomorphism, people talk about things like the projection formula or Frobenius reciprocity, which sometimes means other things, or something being a Hopf adjunction. It's not really important what these words are, but the point is, like, this is something we're interested in, of studying how maps like this correspond to different morphisms that relate tensors and internal Homs. So we're interested. It's interesting to study this idea of mates involving these multivariable adjunctions as well as ordinary adjunctions together. So we'd like to have some sort of abstract framework to talk about multivariable adjunctions and maybe two cells and mates between them. But this turns out to be a little bit trickier than in the case of adjunctions. So adjunctions can be made into the objects of the morphisms of a category, because we can compose adjunctions together. We did that when we were talking about this double category of adjunctions, right? We said that there's the horizontal morphisms are adjunctions, and we sort of implicit in that is the fact that we can compose adjunctions and make longer adjunctions. But how do we compose multivariable adjunctions? So it's maybe just to say the obvious, I mean, a multivariable adjunction is not just an adjunction whose domain is a product of categories, right? Because that would involve a functor back from C to A cross B, rather, and instead we have these two different functors going back, and A and B appear in their domains as well. So it's something different. It turns out that one natural way to arrange multivariable adjunctions into a formal structure is to put them into what's called a multi-category. So a multi-category is like a category where we allow the domain of a morphism to have more than one object in it. In addition to multivariable adjunctions, another example, classical example you should be thinking about is something like vector spaces with multilinear maps. Right, so a multi-category has a collection of objects, and it has Homsets that we usually write like this: M of say A1 ... up to AN with commas, and then a semicolon, and then the codomain. So these objects are all the domain, and this is the codomain. So you can think about this as kind of like an arrow that has a bunch of inputs and a single output. So in the case of vector spaces, then this would be a multilinear map. So it would be a function V1 cross up to Vn to W, which is linear in each argument separately. That would be a multilinear map. And then in the case of multivariable adjunctions, we have a double category, say MAdj, where the objects are categories, and where a morphism, one of these morphisms in MAdj from, say, A1 up to AN to B is an n variable adjunction. So just like up here, this was a 2-variable adjunction. A 2-variable adjunction involves 3 functors and 3 categories. So now an n-variable adjunction involves n plus 1 categories and n functors. So there's an F that goes from A1 across AN up to B, down to B, and then there's a G1 up to Gn. So each of them is going to land in the corresponding A. And it's got, in the domain, it's got a B, and then it's got all the other A's with ops on them. A2 op cross up to AN op cross B, and then here A1 up to AN minus 1. So each of these is an n-variable functor that lands in one of these n plus 1 categories, and then we have Homset isomorphisms like this. So at B of some value of F, mapping into some object B is isomorphic to, say, A1, mapping from little a1 into G1 of all these other guys, and so on for all these other ones. So all these Homsets are isomorphic. So in the 2-variable case, that gives us what we had up here. So when n equals 2, which is what we had before, when n equals 1, this is an ordinary adjunction. Right, if you compile this out when n equals 1, we have 2 categories and we have 2 functors in either direction, and then there's only one possible isomorphism, and that gives us an ordinary adjunction. And it's worth mentioning that you can also take n equals 0. You can have a 0-ary morphism, so an adj from nothing into some category B. So it consists of 1 category and 1 functor. So there's an F, which maps from the Cartesian product of no categories, which is the terminal category, into B. And then there's nothing to say. Right? There are no isomorphisms. So this is just an object of B.
I'm sorry, Mike. There is a question by Paul Taylor.
Yes.
By Paul. So he's asking if you might want to preserve the cyclic order when doing this.
So I'm not being very precise about the presentation. So if you write this down formally in order to do all of the bookkeeping, then you would probably want to be careful about something like preserving cyclic order. Informally, the examples we look at, often we sort of put the opposited ones in the front. That's what I did up here in this example. But yes, it's true that when you write this out carefully to get all the bookkeeping right, you probably want to be more systematic and preserve the cyclic order. You also may want to do something that is more systematic about the placement of the opposites. Right? So here what I've got is, I've got an F that has no opposites at all, and then I've got all the G's that have opposites on all but one of the things in the domain. But there's one more systematic way of doing that is to say, to instead have put all the opposites on the codomain. So you have something going from A1 to AN up to B op, and then you have like A2 up to AN cross B going to A1 op, and then all the way down to, I guess, if B cross A1 up to AN minus 1 going to AN op. So that's right. You can oppositize everything, and oppositize some of your categories and flip them around and sort of make it more systematic. But in the examples that we usually see, tend to look more like this. And so I'm just sort of being a little bit informal but writing it like that.
Thank you. Well, so Paul is saying that he was thinking that the product of the categories might be replaced by a non-symmetric tensor or something like this.
Yeah, it could be. It could quite be. It could very well be. Although I think you might run in. I'm not sure how well it would work to compose everything that way. It might work or it might not work.
Yeah, and there's another question. So in the definition, the B can be replaced by one of the A's, by one of the AIs, I guess. And well, I guess the answer is yes. I don't know.
Can B be replaced by one of the AIs? I mean, it could happen in practice that some of these categories are the same as each other. Just like in a category, you can have endomorphisms of an object. In a multi-category, a given particular object could appear more than once in the domain or also in the codomain. Just like in this case of a closed monoidal category, A, B, and C are all the same category V. Was that the question?
Yeah, I think so. Well,
okay.
Yeah, thank you very much.
Great. Okay, so multivariable adjunctions form a multi-category. And you can take this perspective and write down a formal structure which will allow us to talk about multivariable mates in a formal way. And this is in fact what Eugenia Cheng and Nick Gursky and Emily Reel did. So they studied multivariable mates using a multi-double category, or maybe I'll actually add a cyclic multi-double category. So this is a sort of a version of this double category adj, where now in the adjunction direction we have it behave like a multi-category, and the other direction is just ordinary functors. And then they have a cyclic action on it that sort of represents the fact that we can apply opposites and sort of move things around. I don't want to describe that in detail. You can read their paper, because I want to use a different abstract structure to describe multivariable adjunctions, which I think has some advantages. And this is the notion of a polycategory. So polycategories are, I don't know, maybe a little bit less well known than multi-categories in sort of category theory circles. I certainly learned about multi-categories before I learned about polycategories. Polycategories tend to be better known by people who study things like linear logic, because they're sort of the semantics of classical linear logic. But they're actually really natural. A polycategory is like a multi-category, but it allows us to have multiple objects in the domain and in the codomain. So we have a list of objects in the domain, and we also have a list of objects in the codomain, A1 up to AM and B1 up to BN. So you have a bunch of inputs and also a bunch of outputs. So it's much more symmetrical than a multi-category in that way. Now, saying that, just that I can have multiple things in the domain and multiple things in the codomain is not really enough to specify what a polycategory is, because there are actually lots of different categorical structures that allow multiple things in the object in the domain and multiple things in the codomain. So one of them is what's called a prop, or a colored prop. Another one, there are other things that go by names like properads and various other things like this. So those are different from a polycategory, and the way in which they are different is what sort of compositions you're allowed to do. So in a polycategory, the only kind of composition you're allowed to do is if you have one morphism of these kinds and another morphism of these kinds, and one of the objects of the output of one matches the outputs in the input of the other one. Then you can compose them along that one single object. And all the other objects in the codomain of the first one survive to end up in the codomain of the output. And similarly, all the other objects in the domain of the second one. And so we compose along only one object. Now, this picture that I've drawn here, where I have sort of these strings crossing over each other, might suggest that we have to be using some symmetry here. Symmetric polycategories are a little bit simpler to work with, and the examples that I'm interested in are symmetric, so everything is going to be symmetric, which means that we have a symmetric group action. We have a permutation action on the lists in the domain and codomain. So if I have a morphism from A, B to C, D, then I can swap things around and turn it into a morphism from BA to DC, and so on. There are also non-symmetric versions of polycategories, but they're a little bit fiddlier to work with. For instance, you can sort of restrict this composition to the case where nothing would ever, no arrows, no strings would ever have to cross over each other. Or you can maybe allow them with some sort of cyclic behavior or something like that. But today everything is symmetric.
Sorry, so a morphism has like a labeling, like a morphism, like in the, if you have two morphisms that like the ones that you drew, you keep track of which object you're going to concatenate with?
That's right. You have to choose which object you're composing along.
Okay. Okay. Thank you.
So if this is if this is G and this is F, and this string here represents an object which is A, then the composite, I could call it as F composed along A with G. But I mean, technically, even that notation is ambiguous because the same object A might appear somewhere else. Right? So really, I should be indicating the index at which I'm composing. But usually this sort of thing is sufficient to disambiguate. You could say F compose I, G, or I comma J, maybe, when this is the ith output and the jth input. Okay, so that's the notion of a polycategory. And of course, this is composition is associative and unital and so on. I guess maybe one other thing to notice that you can compose only along one object. So that means you can't do something like this. But you also can't take two morphisms and set them next to each other. There's no sort of tensor product operation of anything like that. So I claim that multivariable adjunctions are a polycategory. And rather than sort of give a general definition, let's just think about a simple case. So what is an adjunction, say, that has two categories in its domain and also two categories in its codomain? So in the case of a multivariable adjunction with one category in the codomain, what we did was we had one functor whose codomain was each of the categories involved. There was one functor landing in the codomain category, and then there was one functor landing in each domain category. So it's natural to expect that the same thing is going to happen here. So we're going to have maybe an F from A cross B cross C to D, maybe with some ops on it somewhere, and maybe a G from, should I try to make Paul happy by being cyclic? I don't know if I can. A cross B cross D to C, I'll just be lazy. And then maybe a H from B cross C cross D to A, and then a K from A cross C cross D to B. And then there are going to be some adjunction isomorphisms. So something like D mapping out of, say, F of A, B, C into D is got to be isomorphic to something like C mapping out of G of A, B, D into C, and similarly other things. So maybe it's not obvious which side these functors go on. But we can sort of make a guess by looking back at this general version of this version here, where the functors landing on the codomain appears on the left of these Homset isomorphisms, and the functors landing in the domain categories appear on the right. So let's sort of preserve that property here. I put my F and my G on the left and my H and my K on the right. And then the need to make these natural tells me where I should put all my ops, right? So if, because C appears on the right here, but it appears on the left over here. So that means I should put an op there, and then I should have an op there. And I guess I should have an op here and an op here or something like that. Is that right? Something like that. Okay, so there's once we sort of sit down and think about the fact that it might work, we can go ahead and write down this notion of a multivariable adjunction, where we have more things in the domain and more things in the codomain. And the way to compose these things is really just the same way that we compose multivariable adjunctions before, because there's some, we're really just doing the same thing as we were before, except that we have some ops in different places. In fact, it's the case that a multivariable adjunction from, say, A comma B to C comma D is really the same as one from, say, A, B, and C op to D, or any other things like that. So I can move my categories from left to right, from the domain to the codomain, by putting ops on them. So in a sense, this is really capturing the same information, but it has certain advantages. One advantage is that it allows us to represent things like contravariant adjunctions in a direct way without needing to put an op into the statement. So take, for instance, what does it mean to have a multivariable adjunction from nothing to C and D? So this consists of a couple of functors, say H from C op to D and K from D op to C, with Homset isomorphisms, say mapping D into H of C. No, sorry, I think it's the other way around. Yeah, H of C into D is isomorphic to C of K of D into C. Right, so this sort of contravariant adjunction arises occasionally, and you have to, if you want to write it as an ordinary adjunction with two categories, you have to choose that it's going to be, say, an adjunction from C op to D. But this is sort of arbitrary. You might as well have chosen it to be an adjunction from C to D op. But with this notion of a multivariable adjunction that can have sort of nothing on the left and everything on the right, or vice versa, then we can represent this directly in terms of two contravariant functors and a Homset isomorphism between them. And we can compose it with other things. So that's one nice thing about this structure. Another nice thing about this structure is that the cyclic operation of applying opposites can happen, has a universal property. So there's a notion of what it means for an object in a polycategory to be a dual of some other object. And I'm not going to say exactly what this is, but I'm going to just draw some pictures. So there's, to say that A op is a dual of A, there's a unit map that looks like this. It maps from nothing into A and A op. And there's a co-unit map, which looks like this, that maps from A and A op into nothing. And then there are some triangle equations that look kind of like every other triangle equation in the world. And this characterizes this A op object up to isomorphism or up to equivalence in this polycategory. So in the Chen-Gursky-Riel situation, the opposite operation on categories is an extra structure on the multi-category that lets you permute things cyclically. But in a polycategory, you can give it a universal property, and it sort of characterizes it uniquely. So working with polycategories, we can express the multivariable mates construction in terms of a poly double category. And these sort of things are a little bit tricky to give names to. You might want to call it a double polycategory, or it's not clear because that kind of rolls off the tongue a little bit better. But the problem with double polycategory is that it sounds like it's got two polycategories. Whereas in fact, what I mean here is that it's poly in only one direction. So it's got sort of horizontal polymorphisms, but then the vertical morphisms are only ordinary ones. And then you've got two cells that look like that. So this is, what I mean here is formally, this is an internal category in the category of polycategories. So it's got a polycategory of objects, which is the objects and the horizontal poly arrows. And then it's got a polycategory of morphisms, which are the vertical morphisms and the two cells. And then it's got domain and codomain and unit and composition maps and so on. So what this thing is, this is a poly double category of multivariable adjunctions. So the objects are categories. The vertical arrows are just ordinary functors. The horizontal poly things are multivariable adjunctions. And then these two cells are mate tuples. So what I mean by that is there's sort of, there's n+1 different two cells, natural transformations, that are related by a Mate's correspondence. And so each of these natural transformations looks like, say, like one of them is going to look like this. There's one that looks like that for the F's. Like if I have a multivariable adjunction on top has an F, and at bottom I have an F prime, and then I can talk about a two cell here. And then there's another one for all of the G's. This is, and then in the polycategorical version, it still works just the same. And there's each, and then the theorem is just like in the one-dimensional case, or the sort of the one variable case, is that any one of these two cells uniquely determines the others. So that's a way of stating this multivariable Mate's correspondence. Okay, so that's great. Now, the last thing I wanted to say, let's see, I have maybe 5 or 10 more minutes. I'm not, was this supposed to be 15 minutes or?
Yeah, 15 minutes. Yep.
Okay, so 5 more minutes or so. Is how can we make this a little more abstract? So the construction of this double category of adj right? This can be done from any two category. For any two category, I can talk about adjunctions internal to that two category, and I have a Mate's correspondence. But it's less clear how to do this multivariable version inside of a two category, because it's not as clear what this sort of, I don't have a notion of op, and I don't have this obvious notion of Homset isomorphisms, where I would have to sort of re-express, if I re-express it in terms of unit and co-unit, then I need some notion of extraordinary natural transformation. So it's kind of a hard problem to figure out the right context in which to do this. But one thing that we can do is we can define something more general, which includes this construction in the case of cat. And this is the Chu construction, which long predates the study of multivariable adjunctions, but it turns out to include them. So here's the idea, is that we have some category, or maybe a two category, maybe I'll call it K, and we have an object, which I'll write as S, because I'm thinking of it as like cat with the category of sets. I guess maybe this should be large categories if I want the category of sets to be an object of it. But I'm not going to worry about size very much. Okay, and then I'm going to try to define some sort of generalized version of this world of the multivariable construction of adjunctions. And I need some sort of notion of isomorphism of Homsets and some notion of opposite. But so rather than regard these as structures on K, I'm going to build those structures into the objects of the construction that I'm going to make. So this Chu category, Chu of KS, its objects are going to be pairs of objects of K. So I've got an object of K called A plus and an object of K called K minus. And I'm thinking about them as like a category and its opposite. But in general, they might be sort of a formal opposite, which may not actually be the opposite category. And then I've got a morphism from, say, A minus cross A plus to S, which I'm thinking of as being like the Hom functor of my category that goes from A op cross A into sets. But again, I'm doing something more general. I'm taking this as the data defining an object of this category. And then I can choose what are my morphisms going to be. So there are actually different kinds of morphisms, and I'm going to define this to be a double category. So the vertical morphisms are going to be like functors between these things that are like categories. So I've got another thing, a B plus and a B minus and an HB. Then a vertical morphism is going to consist of an F plus and an F minus going in these directions, and then a two-cell, a natural transformation, or maybe inequality if K is just an ordinary category, between these functors into S. And so if I'm actually talking about categories and their opposites, then I've got a functor between the categories that induces an opt functor between their opposite categories and an action on Homsets. Okay. So those are the vertical morphisms.
But a priori, there's no relationship between F plus and F minus, right?
Right.
That's an example.
Right.
Okay.
So what there's going to be is that this multivariable adjunctions is going to sit inside Chu of cat set. But it's not going to be everything. There's going to be extra objects over here. And in general object, these things are unrelated to each other. But inside this embedding, I'm choosing them to be the objects for which that is actually the opposite in the Hom functor. Okay. And then in the horizontal direction, I'm going to have not just a category, but I'm going to have a polycategory. So this thing here is going to be one of these poly double categories. So I've got, say, an A1 up to AM mapping to a B1 up to Bn, then to redefine this, I'm going to write down the definition of multivariable adjunction using these sort of formal opposites. So I've got, I'm going to have an F. Well, let me just do the simple case of, say, AB mapping to CD, so we don't have to worry about indices. So I'm going to have an F, which goes from A plus and B plus and C minus to D plus, right? If you look back at what I was doing here, right? I'm just going to turn all the categories that aren't opt into pluses and the ones that are opt into minuses. Right? And then I've got a G that goes from A plus and B plus and D minus to C plus, and similarly things like that. Right? So like A minus and C plus and D plus goes to B plus, and B minus and C plus and D plus goes to A plus. And then I've got some isomorphisms between maps to S. Right? So something like if I've got A plus times B plus times, let me see if I get this right, C plus times D plus, then maybe this should be C minus. Sorry. Then on the one hand, I can do F, and that gets me to D plus cross D minus, and then I have HD maps into S. Or on the other hand, I can do G, which is A plus and B plus and D minus maps to C plus. So that gives me to C plus and C minus. And then I have HC that maps into S, and there's an isomorphism there. And then I have some other isomorphisms like that. So I can make perfect sense of that sort of isomorphism. And then I have two cells, which are sort of mate tuples. Sorry, I'm running a little over. And in this general case, the mate tuples are not determined by a single one, because I don't have sort of the Oneida lemma to sort of reduce them from one to determine the other ones. But I can still have a lot of the same properties that I had for multivariable adjunctions. Okay, so the true construction has a lot of other applications, and if people have studied it because it gives you a model of, say, linear logic and star autonomous categories. It gives you sort of a formal home for dualities. In this case, cat set, you can talk about things like Gabriel-Ulmer duality live naturally inside of the true construction because you can switch the plus and the minus components. You have this sort of natural duality there. But the point, sort of the main point that I wanted to make is that this notion of multivariable adjunction assembles naturally into a polycategory that naturally lives inside this true construction, which is sort of an abstract, can be viewed as an abstract generalization of that. All right, I'll stop.
One. Oh, sorry. Yeah, I think I was muted. I was muted. So yeah, thank you very much for the. And yeah, I forgot to upload. Yeah, are there any questions or comments for Michael? Yeah, there's a few. Paul, yeah, please.
Okay, am I visible now? Just a minute.
Mm-hmm.
Have I turned my
yes.
I get confused with Zoom, I'm afraid, especially different versions of it. Okay, so an interesting talk. It seems rather abstract though. So the thing that I like about category theory, the thing that's really the good PR for category theory, is when you get something which other mathematicians have invented that is very complicated and arbitrary, and then you can show that some very simple construction with arrows in category theory, reproduces the complicated thing that the other mathematicians have done. Now you've shown a couple of examples of these in your multi-adjunctions. Can you show some more convincing examples where there are more than three things, applications elsewhere?
More than three things? You mean like multivariable adjunctions with more than three categories involved?
Yes, yes, or even other examples with three of them.
This is actually a really interesting question. I don't actually know of examples of multivariable adjunctions with more than three categories that don't arise as a composite of ones that involve only three categories. There is, the ability to talk about ones with more categories is useful because, for instance, you might want to talk about the associativity of a binary one.
Yeah. Okay.
Right? So you have some monoidal category where the tensor product is part of a multivariable adjunction. Then you have an associativity isomorphism here, and so then that has mates which tell you about how the tensor product interacts with the internal Homs in some sort of associativity way. And then there's some coherence law for that, which involves four things in the domain, and so on. So that's one example. Another example that sort of shows the value of this polycategorical approach with allowing multiple things in the domain and codomain is in a polycategory, you can define the notion of a Frobenius object, where you have, so this is an object where you have a multiplication and also a co-multiplication. So this is a monoid and a comonoid. And then you have the Frobenius laws hold that if I take two things and multiply them and then co-multiply them, that's the same as co-multiplying the first one and then multiplying that, and similarly on the other side. Okay. In particular, and so the generating morphisms only involve three categories, but the laws you're interested in, like associativity, involve four, and these things are composed in different ways. And you can generalize that to a pseudo-Frobenius object and that make these isomorphisms that satisfy some coherence laws. It turns out that a pseudo-Frobenius object in multivariable adjunctions is more or less the same as a star autonomous category.
Okay.
So is that something that non-category theorists invented? Well, I don't know, it depends who you call a non-category theorist, I guess, or invented, but.
Yeah. Well, they look like neat examples, yeah. Okay, can I ask another question while I've got the floor? Sort of to, so I came here, as it were, to because you were going to talk about tube constructions, and I've been playing with variations on tube constructions myself. I'm wondering where the canonical place is for standard category theory on tube constructions. I know that Vaughan Pratt gets most of the publicity for this, but I was thinking, but he has two constructions over the category of sets. I'm wondering who's Bob Perret might know this one. Who's written the standard things about limits and co-limits, for example, in two categories? What do you know that one?
I mean, there's the original work on star autonomous categories. I don't remember whether the limits and co-limits are in there.
Okay, forget.
I don't know.
Okay, thanks.
Yeah, thank you, Paul. Carlos, yeah, please.
First of all, Mike Shulman, thank you for the beautiful talk. And I have two questions. The first, you mentioned when you talk about multivariable adjunctions, yeah, I think for n equal 2, you mentioned the projection formula. And for people that is study algebraic topology, it's very important, the projection formula, because this depends on the Thom-Pontryagin construction. So I was wondering if you can write the actions maybe in the Giesing or Onker map. So you have in homology and in cohomology the usual inducing maps, but you have a map that go in the reverse orientation. And I don't know if you can write the actions that should satisfy a Giesing map or Onker map in terms of these multivariable adjunctions. You know? And this is my first question. And the second is that if there is an occurrence, so you just also mentioned this, the Frobenius object, but I think that maybe there are some occurrence of this multivariable adjunction or polycategories in cobordism categories.
In which?
In cobordism categories.
Cobordism categories, yes.
Yeah.
Yeah, I don't. For the first question, I don't know offhand exactly what the situation is or whether, but it is the case. I know that there's sort of various general frameworks for sort of pairs of adjunctions or maps that go in the opposite direction or comparing adjoints. And a lot of those can be written in terms of mates of one kind or another. So if you'd like to ask offline with some more details, then I could try to have an opinion or see if I have anything to refer you to. The Frobenius structures do appear a lot in cobordism categories. I think, if I remember, usually cobordism categories are have the, so a polycategory can have sort of two different tensor products. If the multimorphisms are representable on one side or on the other side, those are given by two different tensor products, which make a linearly distributive category. But I think the cobordism categories usually only have one tensor product, which is maybe a disjoint union. So they have more structure, I guess, than a polycategory does. But the Frobenius stuff and the thing that you can do in a polycategory is sort of the stuff that you can do that's sort of topological. It doesn't involve like making holes or loops or something like that. So there is a relation.
But could you mention again what is this framework of the projection formula?
Sorry, what about it?
About the projection formula. When you write it, it was an example of a multivariable adjunction, no?
Yeah, so you have the abstract context in which I was talking about it is you have two monoidal categories, two closed monoidal categories, and you have an adjunction between them. And then there's some map between composites of these adjunction formulas with the tensor products. There's the paper that I always go back to when I'm wondering about this stuff is called Isomorphisms of Left and Right Adjoints by May and Hu and maybe somebody, Fausk maybe. So they talk about some various general frameworks for triples and adjoints between monoidal categories and sort of different contexts in which you could have different kinds of maps relating them. So that might be worth having a look at.
Okay, thank you very much, Mike.
Okay.
Yeah, thank you, Carlos. Yeah, Mehmet, yeah, please go ahead. Well, you had your hand raised, but I think well, go ahead.
Okay, thank you. I just write the question, by the way. It's an internal Frobean object, but is there a maybe simpler definition? It looks, it looks similar to operand or prop to me, but they have very simple definitions like monoid in some pre-ship category over the ordinal sums. So does a polycategory has a definition like this?
Well, I don't know that I would agree that that definition of an operand is simpler. I would say that you've just taken the ordinary definition and wrapped it up into a complicated monoidal structure.
Okay.
But
yeah. Known like in terms of much familiar things, maybe. Yeah, you're right, of course.
Yeah, I don't know offhand whether it's exactly a monoidal structure that you can, that you could write down, but it might very well be. It's a composition operation very much like that in a multi-category or an operand. So there's it wouldn't be surprised if there was some kind of substitution product.
Okay, thank you.
Yeah, thank you very much, Mehmet. Yeah, Arthur, please go ahead.
First of all, thanks for your talk. And I just have a small, maybe basic question about the Chu construction. So I'm not very familiar with it. So I'm wondering if you've thought about, if you take like, I don't know, simple example categories like category of finite dimensional vector spaces, and then you apply the Chu construction, do you get something that's kind of related to like the category of finite dimensional Hilbert spaces or something like this?
Very much so, yes. That's actually one of the motivations for something like a Chu construction. That just like you can embed categories with adjunctions into the Chu on cat set, then if you take an inner product space and map it to the triple consisting of itself and itself again and its inner product, then the morphisms in the Chu construction are these are adjoint pairs of linear maps.
Cool. Okay. Thank you.
So this is the best answer that I know actually to the common question of how are adjoint linear maps related to adjoint functors.
That's exactly the question I was asking.
They're both instances of a Chu construction.
That's very cool. Okay. Yeah, I didn't know that, and it's nice to know that. Thank you.
Yeah, thank you very much, Arthur. Well, yeah, Carlos, yeah, please go ahead. I think you have another question.
No.
Okay. So you left your hand raised. Yeah, in the direction of Arthur's question, is there a way of embedding polynomial functors into Chu spaces?
I don't know.
Sorry. Yeah, no, it's okay. Yeah, I think that's more of a question for David. Yeah, thank you very much. Yeah, Paul, go ahead. I think you have another question.
I was just going to comment on the previous point. So if you apply the Chu construction to a category that's already star autonomous, don't you just get essentially an arrow category of the one you started with?
I'm
just actually, or to make that question more abstract, what is the Chu construction as a monad? What's the multiplication of the monad?
Well, so the
monad, sorry.
The abstract context in which I like to talk about the Chu construction is that. Sorry, just a moment here. Let me get my screen back. Oh, that's weird. there's a, sorry, my full screen mode is breaking. No, I was going to try that. The abstract context in which I like to think about the Chu construction is that there's the category of polycategories, and then there's the category of, you might call augmented multi-categories. So these are essentially polycategories in which the codomain of a morphism can be one object or it can be empty only. And so if you restrict the codomains in a polycategory to always have exactly one object, then you get precisely a multi-category. But if you restrict them to be either one object or no objects, then you get this sort of thing that I'm calling an augmented multi-category. I can call it other things too. When I'm feeling a little bit something or other, I call it a co-subunary polycategory, but I don't know if that's a very ugly word. And then the Chu construction, there's a forgetful functor from polycategories to augmented multi-categories, and the Chu construction is its right adjoint. So it's a monad on the category of polycategories in this sense, but I don't know what its algebras are in that situation. I generally tend to think of it more as in terms of polycategories being the co-algebras for this induced comonad on multi-category, all the augmented multi-categories.
Your polycategories rather look like sequent calculus.
Yes, very much so.
And
they were invented essentially in order to model linear sequent calculus.
Yes. So what you just said, your things you called augmented multi-categories. I can't remember what the results are, but in sequent calculus, there's various ways of restricting it, and you get classical. Somehow phonetically get classical logic by a restriction like this.
Yeah, there's different kinds of sequent calculus.
I've forgotten how it works now, but
yeah.
Yeah, are there any other questions or comments for Michael? Well, if not, let's thank him again for the great talk. Thank you very much, Michael.
Thank you.
Am I the only European? Is everybody else in North America and Central America?
I'm in Europe.
Right, okay.
Me too.
Okay.
Actually, Asia.
I need to go get my supper now.
Who's in East Asia? Sure. Mehmet,
yeah. I mean, very close to Europe, but in Istanbul, Asian side.
Right, quite late for you then.
Yeah, it's night.
Right.
Almost midnight.
All right. Well, good night to everybody.
Okay,
across the ocean.
My thanks for I'm not sure who's in charge, but anyway, the Mexicans were organising the meeting. Right. Okay.
Yeah. Well, thank you everyone for coming, and thank you, Michael, for the great talk.
And thanks for the invitation.
Thank you.
See you later.
Yeah. All right. See you guys. Thank you very much. Gonna have fun.